Okay, welcome to another proof presentation for Math E-156. We are on the last proof for week 1. And in this proof, we have n random variables. We're going to call them x1 through xn. And the idea is that these are all independent and they're all selected from the same distribution. So they are actually IID random variables, independent and identically distributed. So the expected value of all of these is going to be the same. The variance of all of these is going to be the same, and they are independent. Okay, so what we want to show in this proof, our task is to show that the expected value of the sum of each xi subtract x bar square, so sum of those, the expected value of the sum of all of these squares, that is in fact equal to n minus 1 times our variance. So yeah, so the way that we're writing this is variance xi, that's a big X, even if you can't tell. So for all of those, that's sigma squared, and the expected values of each of these xi's is mu. That is a 2, by the way. Okay. So we're actually going to do this in 2 steps. And in the first step, what we're going to do is just take what's inside this expected value here, and we are going to show a different way to express that will be useful to us. So I'm just going to, rewrite this here, and then we'll expand it out and find a different way to express it. That is x bar and the squares on the outside there. Okay, so that is equal to sum over all of this jazz, all this in parentheses, so xi squared subtract 2 x bar times xi plus x bar squared. Okay, so we can break that up. Just take the sum of these xi squareds, xi squared, and then we take the sum of all of these guys. We can take this guy out of the summation on the outside. We can factor him out because he's the same for all of these xi's. So subtract 2 x bar, and then the sum of all of these guys, xi, and summing over all the i's up to n. And then sum this guy n times, well, let's do a little bit of a shortcut. This doesn't depend on I, so it's just going to be n repetitions of that added to itself n times, so plus n x bar squared. Okay. Give myself a little bit more room here. So we can make this look a little bit nicer. Even if my handwriting isn't that nice. So this guy, well, it's the same as x bar, except it's not divided by n, so that's just nx bar, so that's subtract 2, we already had this x bar here, times n x bar plus n x bar squared. Well, we have an x bar times an x bar, so this is minus, I'll write it out, that's minus 2 n x bar, and that is a 2 up there. So minus 2 nx bar plus nx bar is just going to be minus nx bar, so we end up with summation of all of these squares xi squared, that subtract n, oh, there was supposed to be a square there, subtract n x bar squared. Okay, and all we just did was show that this is just another way to express what we initially had, inside of our expected value here. So we're just going to plug what we just found into this expected value operator for the second part of the proof. So this was just pure algebra that is going to make our lives easier. And you will see why momentarily. So moving on to call this part 2 of this proof. That is the expected value of all of this. So sum of all these random variables squared, all the squares of those random variables, subtract n x bar squared. Like we do all the time, we will use the linearity of the expectation operator to rewrite this as the sum of the expectations of these squares subtract n times the expectation x bar squared. Okay, so here is where another little clever trick comes in. Notice that we can, here's actually where we'll do it. We will, here, within these parentheses, subtract the square of the expectation of I, which we can do because we also add them right back in. So there's no net effect there. But and then we will actually also do that, or something very similar over here. Where we, again, going to subtract what we need to get to make this into a variance, as we proved in the first proof from this week. So subtract the square of the expected value of x bar, and then to make sure there's no net effect, we add it right back in. And I just realized that I drew outside of what you guys can see. So, okay. So notice that what I am highlighting here, that is actually just the variance of xi. And we know that the expected value of each xi is mu. So that is actually mu squared. And similarly, this guy, so all the stuff I'm highlighting here, all that is the variance of x bar. And this guy, well, the expectation of x bar we know is also mu. So that is also mu squared. Okay, so I'll write this out a little bit more neatly. So all of this is equal to, oh, well, and we know that the variance of xi, we call that sigma squared, so anyway, so we have this sum from I to n of sigma squared plus mu squared. And that stuff all gets summed here. Then we subtract, so up here, minus n times all of this stuff. So the variance of x bar, we know that to be sigma squared over 2. Or not over 2, I misspoke there, over n, rather. And plus mu squared. And, well, these don't change with the i's, so those are just being added n times, so we get n times all of this. So all of this is equal to, and we'll distribute 2 while we're at it. N sigma squared plus n mu squared subtract, I'll distribute through here, so n cancels that n, so we get subtract, I will write this in different colors to make it a little bit nicer, sigma squared plus n, oh, no, subtracting this, so minus sign also gets distributed, so subtract n mu squared. Well, look, we have that, cancel with that, and we can now factor sigma squared out of this and end up with n minus 1 times sigma squared. And that is in fact what we wanted to demonstrate, so we have finished our proof, and just to remind ourselves, n minus 1 times sigma squared is, going all the way back up here, is the expected value of this sum of these squares. And we are done with this proof.